302. Oh, okay. Oh, neat. All right. Thank you. Chapter 33, number 17. Sounds like a fun one here. And let me get my camera going. And, just gotta turn it on first here. And then screen share. Okay, connect. All right. And that should do it here in a second. While that's coming up, I'll double check here on. Oops. Twice. All right. Nice. Sweet. Okay. All right. Now, let me jump over to the homework problems for your class, 122 right here. And then last time we were in, oh good, we were in chapter 33. So I just need to scroll up to 17. Where is 17? Ah, here we go. All right, so it says here, an inductor, 400 millihenries, and a capacitor, 4.43 microfarads, and a resistor, 500 ohms, are connected in series. A 50 hertz AC source produces a peak current of 250 milliamps in the circuit. Calculate the required peak voltage. All right. So one of the things hopefully you saw in the derivation when you make an RLC circuit was that there was a mathematical relationship that looked a little bit like Ohm's law, in fact, purposely kind of designed that way so that you could just simply take voltage and divide it by, and so in this case, it wouldn't be appropriate to call it resistance, because resistance is a word, that makes heat and reduces the flow of electrons by sucking up some of their energy. But the inductor and the capacitor resist the flow or impede the flow because of the electric and magnetic fields involved. So that's why we like to call those the reactants. And so we have an XL and an XC. And it's the combination of the three of those that lead to the overall, and I like to just use the word opposition to the current flowing, what is stopping the current from flowing. Now, they play different roles because of the electromagnetics involved. And because of that, you don't just simply add them together. Too bad. That would make it a lot easier. But we did go through a little phasor diagram and come up with that the impedance or reactance, I should say, of the inductor and the capacitor are opposite of each other. So you subtract the two, and they're at 90 degrees in terms of a phasor diagram. So when you combine the effect of resistance and reactance, we call it impedance, but to get the total, you have to kind of add them like you would two vectors that would be at right angles to each other. So you have to do a Pythagorean theorem. We call this addition in quadrature. So we've got to add the effect of all of them. Okay, so in our case, they give us the frequency. That's important because the reactance of the inductor is omega L, and the reactance of the capacitor is 1 over omega C. So in order to figure out the reactance of these two, you need to know the frequency and their value of the inductor or the capacitor. And we know all those. In this case, they give us the peak voltage. So maybe I should put here, if you put in maximum voltage, this will give you maximum current. The same equation applies, by the way, for RMS if you wanted to do RMS. But since our question, or at least A, I haven't really gone on to B yet, but A clearly says calculate the required peak voltage in order to get this peak current. So let me just calculate the impedance here. So let's see, going back to the resistance, this is 500 ohms. Okay. The reactance of the inductor, maybe I'll just do a separate calculation for that, would be the omega L. So that'd be 2 pi times 50 times the L. And what was the L in this? 400 milli. All right, so grabbing my calculator for the reactance of the inductor, 2 times pi times 50 times 0.4, give me about 125.7 ohms. So 125.7 ohms. I'll put it up here, 125.7. Now the reactance of the capacitor, and the capacitor was 4.43 microfarads. So if I just do the denominator here, this is 2 times pi times 50 times 4.43 micro. Take the reciprocal of that, and we're looking at about 718.5 ohms. All right, so let me put that in this equation, 718.5. All right, so now I can actually then do this calculation and get the impedance. So I think I will go up and grab that 125.7. I will subtract off the answer I just got. And so that's about a negative 592. Let me square that and then add it to 500 squared. And then finally taking the square root of all of that leaves me with an impedance of 775.6. Okay. So that's really what I think this question centers around, is saying, hey, did you kind of understand the series RLC circuit? And with that in mind, then I can actually come over here and then put the maximum current. Let me just double check that number. I think they said 250 milliamps, okay. And now that would correspond to a maximum voltage, and then I can divide it by an impedance of 775.6 ohms. So the three of these guys together, you might say, are the equivalent of a resistor of 775.6 ohms. Although probably shouldn't say it that way, because the inductor and capacitor act so differently in many other aspects. But in terms of opposing the currents, that's what they are equivalent to. All right, so I'm going to take that number and multiply by 0.25 and get 194 volts. So I guess I would say that for part A, anyways, where it says what is the peak voltage, and there it is. I would need 194 peak voltage as an AC source in order to get this much peak current or maximum current of 0.25. Now there's a part B to this. So part B says, determine the phase angle by which the current leads or lags the applied voltage. All right, so another interesting effect, very different than the resistors, is that the current and voltage aren't necessarily in phase. They don't happen at the same time. And so the angle that one leads the other was given by the difference in these two. So the positive numbers is what we get from an inductor. And so an inductor, we have that, I like to use the word Eli as I was explaining in the lecture, because of Faraday's law, voltage would lead the current, and Eli is a good way to kind of describe that, because you got the L for the inductor, and then you've got the E for EMF, which is before the I for the current. And so anything that is behaving like a more of an inductor would then say that the voltage comes before the current. But anything that is then, and so another nice phrase is ice, because again, we can use the C for the symbol capacitor, and then the I comes before the E. And this one's hopefully pretty obvious too. I mean, you have a capacitor, you're not going to get an EMF, you're not going to get any voltage on it till you actually put charge on it. So you got to get current, you got to have the current flowing before you have anything in it. It would be like saying, you know, if you're filling up a bucket, which would come first? The flow into the bucket or the filled bucket? And obviously the flow's got to come first. And so we got to have current first, that's the flow, and then it builds up in the bucket, and the charge that builds up is what makes the EMF. So for in a capacitor, the I is before the current is before the EMF.
Could you go through that one more time for what the ELI was again?
What it stands for?
Yeah.
Okay, so the Eli, I'll make it a little bigger here. Eli is just a good way to try to remember which comes first in the inductor. Now, I know it's inductor because it has the L in it. And as you see the word Eli, there is an EMF first, so the E for the EMF, and then the I for the current. So voltage comes before current in the inductor. Now,
thank you.
Yeah, so that I was going to say, and the same thing from the physics, but I don't think that was your question. You know, your question was just the symbolism here. And I'll say the same thing for the ice. Ice, I'll just write out the word ice again, is kind of a nice way to try to remember which comes first, the current or the voltage, that is the EMF. And so imagine the middle letter, the C, representing, hey, this stands for a capacitor. And so in the capacitor, the first letter is the I. So that tells me current comes before the EMF, comes before the voltage. So you get current before the voltage in a capacitor. I know it's a capacitor because it's C. I know it's a current before the EMF because the I comes before the E. And of course, as we just said, for the Eli. So fun little book is called Eli the Iceman. It's got a little cave, and Eli is kind of this short bearded guy. Anyways, and so it's a little kind of a fun cartoon book on understanding AC circuits. And the title of it is Eli the Iceman. So if you have a few moments someday this weekend, just go to Google and Google Eli the Iceman, and you'll see all these crazy images, and the poems come up too. Actually, the poem's really good. And so I'd encourage you to look up the poem and read it. yeah, it's written in prose and it's real nice and helps you remember which comes first. It talks about remembering my name, Eli the Iceman, or something like that. Okay, so back to this problem, and I have to go here to page 2. But you could have even seen it in the numbers. I should have pointed it out here. But as I was looking at this, I realized that the reactance of my inductor is much smaller than the reactance of my capacitor. So that would tell me that this circuit is being mostly opposed, if you will, from the capacitor. And that tells me something really important here. It tells me that the capacitor is dominating everything else in this circuit. I look at the number. The resistor, it has only 500 ohms, and it looks like the reactance of the inductor is only about 126, but the reactance of the capacitor is up in the 700s, so 718. So that would tell me that this circuit is dominated by the capacitor. It's not to say it is only a capacitor, but it is certainly dominated by the capacitor. And so because of that, as I go down to think about if it was purely just a capacitor by itself, the current would have come first and then the voltage. And so that would tell me that the current leads the voltage. And that's without even doing any numbers. But I'll go ahead and do the numbers. So as I got sidetracked and I didn't finish my equation, here is the reactance of the inductor, the reactance of the capacitor, and the resistance. And if we solve this equation, we're going to get the phase. And that's going to tell us then what's happening in terms of the current and the voltage. So I'm going to put an inverse tangent so I can get phi by itself, so inverse tangent. And then this would be the reactance of the inductor, which we said was 718.5. Oh, no, sorry, that was the capacitor. The inductor was the 125.7. The reactance of the capacitor was 718.5. And then, of course, the resistor was the 500. And these are done in real numbers here. I guess it wouldn't really matter if I take the inverse tangent. I'm not taking a tangent. So I'm just kind of wondering if I should use my calculator in degrees or radians. I'm already in degrees, so maybe I'll talk degrees. So if I go 125.7, wait, I better be careful. These are real numbers. My bad here. Let's go to radians. Okay, so this is a 125.7, and I'll subtract off 718.5. So there's a negative number. Then I'll divide that by 500, and so we have a negative. And that too is the same reason I would say, okay, the current is going to be in front of the EMF. But now let me do the inverse tangent of that answer. And I get a negative 0.870 radians. This might be a little bit better in degrees. So let me go times 180 divided by pi. And so negative 49.9 degrees. So the negative tells me then that the current is going to come first. So that's ultimately what this question was about, I think. It said, determine the phase angle. Okay, so I did. So the phase angle is negative 49.9, by which the current leads or lags the voltage. And so the current leads. Or to put another way, the voltage, because that's really what we've solved for in this equation. We solved for voltage. The voltage is a negative number, so the voltage lags. And I should probably check this one with the solutions. So don't mess you guys up too much. Although that's kind of the fun part of teaching, when you really mess a student up. No, just teasing. But let's see. So A was 194 volts. Good, that matched. And then B says negative 49.9. Good. And then says that the current leads the voltage. Or another way to say the same thing is voltage lags current. But the question deliberately asked about current. Does the current lead or lag? So I guess we got to answer it in terms of the current. Nice. So good. Hopefully that one made sense, Anthony. All right. So if so, I will go on to, let me write this down. Looks like chapter 32, number 61. And I'll mark the time, 24, so I can put out the Zoom recordings a little better. Okay. And maybe to save me at least a half a sheet of paper, I'll tear that one off. And I will just put on the top of here, chapter 32, number 61. Okay. So let me go back to my PDF and your guys' class and scroll up. This would get us back into chapter 32. Oh, yes, and it's the second page of 32, the one that didn't show up on the PDF that I sent out later. And I just printed myself up a hard copy because I apologize for that too. The correction I made was then scanned at at 90 degrees. So I got tired of looking at that the wrong angle on my screen, so I just printed it up here. All right, but 61 is this one right here, and just kind of looking at it, I see that I've got a power supply, and it looks like I've got a resistor, two resistors actually, and an inductor, which would make sense. This is what chapter 32 is about, to teach us about the inductor. Okay. And first we did inductors with resistors, then later on we did inductors with resistors and capacitors. But we always had a DC voltage. We never left the DC voltage until this next chapter, so this week's chapter, which is 33. Anyways, so in figure 61, so in this is figure, the switch is closed at time equals to 0, and a steady state condition is established. Okay, so let me just check this out here. So we're going to close this switch, and steady state is established. In fact, I'll pause on the rest of the question for a moment. Not that you should, when you're doing a homework problem, you should read it all the way through and then come back and start tinkering with it. But what I want to do is pause so you can kind of see what I'm thinking about right away, just after that sentence. And after that sentence alone, I'm thinking, okay, so the switch has been closed. The switch has been closed for time less than 0, and then for a long time, really, steady state. But this is the part that I'm thinking, that right here, I could ignore the inductor. Remember that the voltage on the inductor is minus L di dt. And so if you didn't catch this in chapter 32, when we have an inductor in a DC circuit for a long period of time, there's not going to be any more changes going on. We can safely say that there is no voltage change on the inductor, which is the same you get for a wire. So after a long period of time, we can just replace the inductor with a wire. It's kind of the reverse of what we did with capacitors. When we had a circuit like maybe this, where we had a capacitor, we said when you first, I should have put a switch in here. When you first close the switch, there's no charge on the capacitor yet. And with no charge, there'd be no voltage. And so you can just replace the capacitor in your mind for that moment. You can say it is just a wire. And so right when we closed the switch, we treated the capacitor as a wire. And I'm saying the reverse for the inductor. I'm saying for the inductor, you can treat it as a wire after a long period of time. In fact, as a side note, after a short period of time for the inductor, but a long period of time for the capacitor, you consider it kind of an open circuit. So for the capacitor, we said after a long period of time, you would think of it as a break in the wire. And that's because the capacitor would build up charge and would eventually build up to get a strong enough field in there that it wouldn't let any more current go through. The inductor is the opposite. In a short amount of time, when you first close the switch, it doesn't want to change the current very quickly. So in other words, if you tried to change the current very quickly, you would get a huge back EMF. And so the inductor creates its own back EMF so large that it will stop the current. It will be like an open circuit. And so that's the neat thing about capacitors and inductors. That's why they're taught in the beginning circuitries, because they do exactly the opposite. And so by combinations of them, you can start with a resistor and go more towards the inductor, or you can go more towards the capacitor, or some kind of combination. And so they have the same effects but reverse. Anyways, so I know I still need to read more on this problem here, but what I am trying to say here is kind of the first thing that went in my mind is, okay, this battery is 18 volts. This resistor up at the top is 2K. This resistor over here is 6K. So I'm thinking after a long period of time, this loop would be 18 minus 6,000 I in this loop. I'll call it I1. Has to be 0. So I1 would be 18 over 6,000, which would make 3 milli. So even without doing too much work and really I've drawn this for you guys to see it, but I would have said, okay, if this is closed for a long time, I would have 3 milliamps going around this loop. And the same logic going around the right-hand loop. I would have 18 minus 2,000, and I'll call this current number 2 over here equals 0. So when I go to solve this, I get current number 2 is 18 divided by 2,000. That would make 9 milliamps. All right. So I drew it all out, but they gave us easy numbers. 18 divided by 6, that's where I got the 3 milliamps, and 18 divided by 2, that's the 9 milliamps. So when I first read this, I said when the switch is closed and the steady state conditions is reached, I look at this picture, I ignore the inductor and say, okay, this direction is making a current of 3 milliamps, and this one is 9 milliamps. So that's what I already got in my head, well, once I read that first sentence. Of course, the switch is opened at time t equals to 0. So now here's where the effect of the inductor is going to play out here. Where I'm going to say, okay, what is going on in this in the inductor? And maybe I have a little more room on page 1 here to kind of say, okay, what is question A? And question A says, find the initial EMF across the inductor immediately after time equals to 0. Which end of the coil, A or B, is at a higher voltage? All right, so now I better go to the next page and actually draw the real circuit, if you will. The real circuit is this 18-volt battery, although the switch has been opened, so it's kind of out of the picture. And this 2 kilo ohm is now going through this inductor L. And the other resistor, which is the 6 kilo ohm, circles around here. So I would say, and this is kind of what I was referring to earlier on about the inductor, I did this argument to say after a long period of time, but I also said after a short period of time, it would make a voltage. And here's the idea. We got this from the energy in the inductor that says you can't really change the current instantaneously quickly in an inductor because of this fact. If this is the energy, then changing the energy quickly would need a lot of power. So you would need a lot of power in order to change the current. You might say this, to change the current really quickly, this number would be huge, which would require a huge amount of power. Since we don't have this huge infinite amount of power, that tells us the current doesn't change instantaneously. It does change, but it's got to be a continuous change.
Would that amount of power be like a nuclear power plant or something to change it?
Well, yeah, I guess this is saying the more power you have, the quicker you can change it. But you can never change it instantaneously. You could never go, and in this case, this is my point, we already set up that there is 9 milliamps going around this right-hand loop. So when you open that switch, it could not go from 9 to, say, down to 7 instantaneously, or 9 down to 0, because a change instantaneously is really kind of an infinite derivative. So it takes an infinite amount of power to change this infinitely quickly. And so we take advantage of this math right here and say, because of that, we will know that the current will change quickly, but not instantaneously. So if it is at 9 amps, a moment after you open the switch, it's still at 9 amps. Now it's changing quickly. So it's going to go from 9 to 8 very quickly, perhaps. And of course, how quickly is yet another question we can begin to discuss. But we know immediately after it is 9. So here's the logic. The logic is then, if this is point A on the diagram, no, sorry, I think I got that one backwards. This is point A on the diagram. This is point B on the diagram. Oh, and I should have put the inductor is 0.4 henries. In order to keep the current going around here, B would have to be at a greater voltage than A. So I would say voltage at B is greater than the voltage at A. You might say then at this point, because of Faraday's law, this little device right here is acting as a battery. And I guess then I would have this kind of circuit. But it's the direction of that current that would answer the first part of this when it asks, how did the author phrase it here? said, find the initial EMF of the inductor at t equal to 0 at the end of the coil, and is A or B at a higher potential. So to keep this current flowing, I would have to have B, the plus side, and A, the minus side.
Okay.
So that would kind of be my argument of, okay, how do I know which one has a greater potential? Now, the other thing I would do is say, okay, to get that voltage, and in my mind, I'm just going to think of this as a momentarily power supply. Of course, it's going to change, but at that moment, I've got to keep this current of 9 milliamps flowing through this inductor. So if this over here is a 6K and this is a 2K, those two together are the equivalent, because they're in series, of an 8K. So I'll just think of it as 8K here, but I could do this, that the voltage between on the inductor, so I'll just say V, what we're trying to solve for, minus 8,000 times the current makes the loop. Now, the 8,000 and the current is 9 milliamps. Then I'm going to play this little game. An 8 times a 9 is a 72. And this K is 1,000. And the little m is 1,000th. So they cancel each other, if you will. Equals 0. And so that says the voltage needs to be 72 volts. So in order for this to work, there's got to be enough voltage created by this inductor to equal 72. That's one of the things that make electric motors a little challenging, because to make an electric motor, you want to run electricity through all these coils, which has an inductive effect. And then if you go to shut off the motor, the voltage that builds up in it can be really large. And if it's too large, it can damage the components that made the motor. And so turning off an electric motor is usually done with what you call a shunt resistor off here on the side. It's high enough so that when the motor's running, most of the power goes to the electric motor. Very little of it goes to the shunt resistor. But when you open it, that shunt resistor is designed so that it will swing around this way and allow current to go through so that the back EMF doesn't have to jump up real high. Otherwise, you can get so much voltage in your motor. Because notice, if this was a motor, I'm creating 72 volts, but I only hooked it up. I was only running it with an 18-volt battery. So maybe like this was like a hand drill. One of those cordless hand drills off on 18 volts. And I'm running this on 18 volts, and I shut it up. All of a sudden, boom, I've got 72 volts in my circuit. And that's with the shunt resistor. So I probably design it this way so that when I'm running my battery and my motor, I'll leak a little current this way. Not that I want to leak the current that way, but so that I can shunt it this way so the voltage only jumps up to 72. If this resistor was greater, then this number would be greater. So there's a trade-off here. When I'm designing it as the electrical engineer, I'm like, okay, how big do I make this resistor? If I make it big, that's good, because I don't drain my battery, because I'm trying to use my battery to run my drill. But on the other hand, when the operator turns it off, the higher this is, the more voltage they create, and so the more I have to make sure my motor can handle that higher voltage. So it's part of your design criteria. Okay, how do I want to do my electrical engineering here? Well, I digress quite a bit from the problem, but I think I've answered the first part. Which one is bigger, B, and what is that voltage? It is 72. And actually, if I can digress just a little bit more, remember that voltage is to be creating by the inductor. So if I put 72 for the voltage that's being created right when I open that switch, and I put 0.4 henries in here, I could actually solve for another interesting part of this problem. At what rate is the current changing? So in other words, I just did the part that said, well, when I open that switch, it's going to do whatever it can to create enough voltage, which apparently turns out to be 72 volts. It's going to create the 72 volts so I can keep the current at 9 amps. But it's also going to be changing quickly. It's going to be decaying away. And I can actually then solve for that. I can actually then take the 72 and divide it by 0.4 and get 180 amps per second. So it's losing its current at 180 amps per second, which of course we're only at 9 milliamps. So it's only going to take a fraction of a second before there's no more current here. But it will take a while, albeit a fraction of a second, before the current completely goes away in this inductor. And that was for free. So let me cross it out because I don't think they ask at what rate is the current now decreasing. They just ask for the voltage that would be created on the inductor, and I treated it as a motor that would then keep the current going around at this 9 milliamps. Okay, so with that in mind, I probably should go to part B of this problem. It says, make a freehand graph of the currents in both R1 and R2 as a function of time, treating the steady state direction as positive. Okay. So what do they call number one? So number one is this 2 kiloohm. So let me do the 2 kiloohm first. I will make a graph. And let me just read it again. Draw a freehand sketch. Okay. So that's good. Freehand sketch or graph of the currents in R1 and R2. And go ahead and treat the steady state direction as positive. Show values both before and after 0. All right. So as we said earlier in the problem, before the switch is open, we reached a steady state for number 2 at 9 milliamps. So if in my graph I use each line as 3, this would be 369 in units of milliamps. And so for time less than 0, I would have 9 milliamps. Of course, somewhere over here we had to turn on the switch, but I won't graph that. So I'll just say, okay. So for all times less than 0, the switch was closed and we had 9 milliamps going around the right loop and 3 milliamps going around the left loop. But I'll worry about that one. And they said in the direction of steady state, so I made it a positive 9. Okay, then as we kind of argued is we would then open this, we would have an LR circuit where the L is the 0.4 and the R, as we said, would be these two together would be the 8,000 volts. Now, we learned then that the current in an RL circuit would decay away really with the same kind of mathematical equation that we had for the capacitor. And so it's an exponential decay. And so it would go from 9 and decay to 0. And it would be an exponential decay. And of course, we could actually then put some numbers in here. We know it would start at 9 milliamps. That was kind of the basics of the whole question, that the inductor will keep it at the steady state and then decay away from there. So it's 9 when the switch is open. So it starts at 9 and then decays away. And then the decay constant, the decay constant is the L over the R. So this would be 0.4 divided by 8,000. And maybe I should just stop right there, because they say just freehand sketch it. So it doesn't really matter what the number is I get for my decay constants. It's just that's what it's going to do. Just a matter of how much time it decays. Well, actually, maybe I'll do this. I know that it drops down by 63%, which is about 2/3. So it's going to be at about 3 milliamps in one decay constant. Wait, I think I said that wrong. Let me try that. E to the -1 should be about 0.37. So that's about 1/3. Yeah, 1/3 left over. Okay, yeah, I did say it right. Okay, so in about one decay time, so when the time is equal to the decay constant, I would get e to the -1, and that would be multiplying 1/3 by about 9. So this right here on the time axis would be one decay constant, which would be about 0.4 divided by the 8,000. So this would be about 50 microseconds. So again, if I was kind of freehand sketching it, that's I guess what I would do there. And of course, that's R1. And then let me need another page here for R2. But the R2 is the other resistor, the 6 kilo ohm resistor. I have time and current. Now, way back at the beginning of this problem, for this left-hand side, we said the steady state was 18 divided by 6. So we got the 3 milliamps. And the problem said, treat that as positive, the direction it was going in steady state. So if I use each division as 3 again, this is what it would be doing for times less than 0. We would be at 3 milliamps. And this is kind of interesting, because coming back to our circuit, remember I said that you couldn't change the current instantaneously, and I hope you caught this part, instantaneously in an inductor.
Yeah.
That doesn't say anything about the resistor. So resistors didn't have this energy storage. So you can change them instantaneously. This argument does not apply for resistors. By the way, for capacitors, we did the same argument, that you couldn't change the voltage instantaneously.
Okay.
But we never had anything like that for the resistors. So we can easily change, and it doesn't take power or energy to change the direction. They just go from one way and the other way. Okay. Now, I guess technically these are moving electrons. They do have some mass, So you might say because of mechanics, you've got to have some kind of acceleration, but that is so minor that I will put a connecting line, but it can be incredibly steep, and the change in the current and the resistor is possible, very steep with very little power. And of course, the reason that's important is because in part 2 here, if you open the switch, this 9 milliamps could no longer go up and around like it's been doing. So instead, the 9 milliamps moves across to the resistor here, the shunt resistor, if this was a motor here, and you go across here, and that then means it goes the other direction. And it goes up to 9 milliamps. So it was going 3. Now all of a sudden, it'll be going, and I'll call it negative 9 milliamps. And this is the part that I was saying is in a math class, you know, you might do a discontinuity here, but in reality, it does have some inertia. So I probably should say that the current changes very quickly.
Yeah, this isn't a math class, right?
And so, yeah, being a physics class, I should really say it really is changing. So I am going to draw a solid line that connects it that has a slope of nearly negative infinity. But I'm not going to worry about having a huge slope because I don't have this issue where the slope of the current would be this issue where the slope of the current would be related to the power. I don't have that for the resistor. Although, like I said, because they do have a little bit of mass, it's somewhat related there. All right, now once I get to that, now we're just back to the problem we just actually did. Is we saw it decaying away. They're in series. It's just we would be defining it as the opposite direction. So it would decay away, and the same thing, it would go down to 1/3 of its value in one time constant, which was roughly 50 microseconds. And so definitely going to decay away. But I think that's why the author made that very clear in the problem. Treats, how do you say it? Treats, make a freehand sketch. Yeah, treating the steady state directions as positive. Because I think he really wanted you to see that it would be a continuous function for the inductor, but a non-continuous function for the resistor. And the resistor is going to change directions before it decays away. So we've got a decay from the negative current on to 0. And I think there's even a C to this problem. At what moment after time equals to 0, does the current in resistor number, and they say 2, but remember at this point, 2 and 1 are in series. So it doesn't matter which one we talk about. But current number 2 having a value of, hey, why did my phone cut out? Well, I'll reconnect you. But after we're looking for what moment in time. So we're looking for time when the current is 2 milliamps. So let me reconnect my phone here. We'll write out this equation.
Definitely have a lot of studying to do still.
Same.
Feel overwhelmed?
Same.
Well, it's probably more so true this semester, but in a regular face-to-face setting, that Tuesday before Thanksgiving, which I guess would be the last lecture, and in this setting right now, it would be the next lecture. I say it jokingly, but I mean it kind of seriously that, all right, here comes Thanksgiving. I'm sure you have lots to be thankful for. So, go to your Thanksgiving dinner, and as soon as it is over, skip the football and start studying. Because we're at the end, and there's just the right weekend, and then that next week is a test, and the week after that's the final exam. So it's a brutal reality.
Yeah, problem is I'm in charge of cooking a few things for Thanksgiving dinner, so.
Well, wait. Well, at least in our family, people who cook don't clean. So
Yeah,
you cook it, and then you get on your homework and let the other ones clean. Visit for a little bit. Got to say hi to everybody. But actually, in this world, I know for us, we've canceled all of our Thanksgiving plans. We just decided it was too risky, and especially for my dad who's 89, and just my mom who's 82. Like, for your sake, and they're kind of torn because they're like, well, hey, you're doing this for our sake, but we want to get together. They're like,
Mhm.
look, we would feel bad, especially the grandkids, because they're at college. If they come home from college and they, pass on the virus and you get sick, your odds of not surviving the coronavirus are pretty high. So, let's not mess with that. We don't, they keep saying on the news, we don't want to have Thanksgiving dinner with a Christmas funeral. That's just not the way to go.
Yeah.
So, but of course, at their age, they're like, hey, this might be our last Thanksgiving anyway. So you never know, coronavirus or not. So, anyways, but every family's got to kind of deal with that. So that's our approach. So we just, okay.
Yeah.
We're hoping we can all see each other maybe in February or something. This vaccine gets going.
Yeah. Nice thing about Lompoc is it's a really, the way I describe it is it's a country surfing town.
Ah, okay.
And my grandma lives in the same town as us, so she's coming over, but we're still going all out for Thanksgiving food because both my parents are still here, and then my grandma. So, yeah.
Yeah.
And
Well,
she's not having to mix it up any more than normal because she lives there already.
oh yeah, good point. You guys probably mix it up normally anyways, huh?
Yeah.
But yeah, then yeah, I mean, if we got together, it would be with my cousins who are all off at college. My kids were all off at college. And cousins on both sides, my wife's side and my sister's side. It's like, yeah, we would get 1, 2, 3, 4, 5, 6, 7, 8 college kids together from different colleges from around the country. It's just a petri dish, I think.
Yeah. I can see that.
We're just not going to do it. All right, we can FaceTime each other. Could even have a family Zoom. We haven't done a family Zoom stuff, but the grandma and grandpa can do the FaceTime just fine, and they're good with that. So they'll FaceTime me, and then separately my sister. Yeah. Okay, I guess I digressed here a little bit. So what was I doing? Oh, the camera went out. Okay, so it had said how much time did it take to get to 2 milliamps? And so we kind of set this one up already. I'll come back to our drawing here. This was the decaying current in the inductor. So what do you start with and what do you decay with? And I kind of talked about it because I added some more things to the graph. I'm curious. I'm going to look at the answers. They probably didn't need this much detail on the graph, because you'll still need this equation for part C here. So I'm going to put 9 milliamps for my initial current. And what I'm doing is I'm trying to find the time when it's 2 milliamps. And so I'll leave T as the unknown, but I need this time constants. And I'm just going to double check here. I thought I said it was 50 micro. Yeah, so 5 times 10 to the minus 5 is 50 micro. So I'm going to put here 50 microseconds. All right, and then so now I've got a little math to do. Milliamps cancels with milliamps. This side becomes a 2 over a 9 e to the minus t over 50 microseconds. To get rid of the e, I take the natural log. So the natural log of 2/9 would then become negative t over 50 microseconds. Bring the negative and the 50 to the other side. And, oh good, ln of something less than 1 is negative. I was getting worried about that negative, but 2 negatives are going to make a positive, okay. And so grabbing my calculator here, negative 50 times the natural log of 2 over 9 comes out to be 75, and in units of microseconds. And that actually fits really well with my graph. My graph, I said it would go down to 3 milliamps in about 50 microseconds. And so it's going to be more than the 50 microseconds.
Cool. That helps a lot. And I just checked the answer for that, and it's 75.2 microseconds. So.
Oh, yeah, 0.2. Yeah, okay, good. Oh, good. And then did everything else check out? The graph?
Yeah, you got the same graphs, it looks like, and then
You got the 72 volts?
Yeah.
Nice. Okay, I won't even bother to look at it then.
Cool. That explains a lot.
Yeah, good.
Okay. I gotta go. I hope you guys have a good weekend.
Okay, yes. Take care. All right. So moving along here. That was a good problem. Digressed quite a bit, but it had a lot of detail in it. That was a good one here. All right, let me go back to the chat room here and see who's after Daniel. What number was that? 61, and then Daniel. Ah, okay. Andrew. 34. Wow. Chapter 34.
All right, 33.
Yeah, I think, yeah.
Oh,
he
okay.
mistyped.
I see. Okay. Good. I keep reading ahead here. Okay, so chapter 33, number 46 at time 4:05. Okay, so chapter 33, number 46. Okay, and 40. Oh, I bet 46. I gotta scroll down because we were in 32. Yeah, okay. 33, 46. Consider these filters. Okay, let me actually say something as I get started. I love this problem. I wish we had more time to do it, but we're starting to get a little more of circuits engineering at this point than is really necessary and required for a physics class. Let me look at the textbook. I think this is section I want to say in my mind 7. Let's see. Here's section 6, power. No, 7 is RCL circuits. 8 is transformers. 9. Here we go. 9 is filters and rectifiers. Okay. So this section, section 9, please know this then, that this is the part in the video lecture I said would be nice to cover, would be nice if we had more time. I'm going to do it now because you're asking. I put it for some homework assignments, but I'm going to put this in the category of like some of the other problems we came across, that this is kind of the transition problem, material that goes to your next level, your next class. And in fact, Andrew, I think you are in the circuits class, if I'm not mistaken. So this is kind of the thing.
I'm actually not in circuits till next semester.
Ah, okay. So who was I thinking? Maybe it's Daniel?
Anthony.
Anthony, yeah, that's what it was. Yeah, we'll start with an A, that's it. Okay. So, yeah, anyways, all right. So you would, so you're going to do it next semester and you're going to talk more about this. And so it's good to see it. It's good that I work through with it. It's good that you read about it. It's good that you do homework on it, but no, it's not on the test, okay? And so this section 9 is not anything I would put on the test, okay? Okay, so with that in mind here, let me come back and look at this problem. It says, consider the filter circuit shown in active figure 23A. Now, I'll draw it here, but 23A, and for whatever reason, need to.
It's on page 943.
943, okay.
Yeah, it's one of the pictures from the like actual chapter, not like a homework picture.
943. My PDF just crashed. I was going to start it up, but I'm just going to look in.
I can just explain it to you.
Oh, okay. Is it a resistor first or a
It's
capacitor?
resistor first and then a capacitor.
All right. So it does a resistor first, and then it does a capacitor like this.
Yeah.
Okay.
And then wires coming out the sides with the V out.
Yeah. Okay. So I'm going to use a phrase that I didn't use too much time. It's more of a circuits phrase called a divider, a voltage divider. In other words, before I do this problem, what if I had done this? What if I had done a problem that just had a voltage V? And so since I'm going to go all the way back to chapter 28, and I'll put resistor number 1, resistor number 2.
In the diagram, real quick, the top diagram, the V, what's the subscript on the V between the two open ends?
Oh, out. O-U-T.
Thank you.
Yeah. And so the reason we like this phrase called a voltage divider here is if you measure this voltage coming across this element, which in mine is resistor number 2, and I'm going to try to direct that back to the capacitor here in a second. But if I were to look at the voltage, and we like to use the phrase, the voltage across the resistor number 2, I would do something like this. The voltage across number 2, which is what I'm measuring, so the voltage out, would be the current times resistor number 2. Okay, well, how would you get the current? Well, the current would be the voltage that you're putting in. And so voltage in divided by, and the current would just flow around. These two would be in series. So it would be R1 plus R2 times R2. Okay. So what we would say is that the voltage that you get out is R2 over R1 plus R2. Now let me pause right there. That's a fraction. The bottom is always bigger than the top. So we call it a voltage divider because depending on the values of R1 and R2, the voltage out is some number between 0 and 1 of what you put in. So if what you're putting in is, say, 9 volts, you can adjust it so voltage out is anywhere from no voltage, if you had 0 resistance for R2, to 9 volts if you had 0 resistance for R1, because then R2 over R2 would be 1. And so we call things like this a voltage divider because they actually give you some kind of voltage and the ability to control that voltage on this value. Maybe a good example of a voltage divider is if you ever try to charge your phone in your car. Your car is 12 volts. You plug it into the cigarette lighter or the utility plug, but you need 5 volts for your charger, for your USB connection that's coming out of there. So we have to take the 12 and cut it down to a 5. And so we divide it a little bit. Now there's fancy ways to do it so you don't lose as much power. So they don't quite do it this simply, but this is a nice voltage divider. Okay, so how does this relate to the more complicated circuit? Let me cross this out. I'm hoping you'll see that if I call this the voltage in, then I'm going to get some voltage out that is some kind of parameter related to voltage in, but it would depend upon the capacitor and the resistor. And what's really neat about this and why we call them filters and not just voltage dividers is because the amount of voltage we get is very much dependent on the frequency. Because remember, unlike this resistor just has a value that depends just on the resistance. This has a reactance that depends on the frequency. That's the neat thing about capacitors and inductors, is that they depend upon the frequency. Okay, so why don't I take this first page and maybe just kind of tuck this away so I can see the circuit, but also I could flip it over and talk about this circuit divider, because watch this. Here's what I would say. I would say, just like I did before, that the voltage out is equal to the currents that I get in this circuit here. So just like I did over here, the currents I got in the circuit times the resistance R2. Now this doesn't have a resistance, this has a reactance. So this would be X sub C. And that's hopefully this first step. Then I go on to this next step. Okay, how do I get the current in this circuit? Okay, well, this is where the chapter 33 came into play with the AC circuits. You would take the voltage that you're putting in and divide it by we like to use the word impedance instead of resistance. And of course, we like that because what is opposing the current isn't just resistance, it's also the electrical effect of the charges on the capacitor. So this opposes the current by resistance. This opposes the current by reactance. The two together is called the impedance. And so the total opposition, the combination of the resistors, the capacitors, and the inductors. Now, this problem doesn't have any inductors, but that's the impedance. And the calculation for the impedance was pretty involved. So I'll just cut right to the derivation of it. We had XL minus XC squared, square rooted. That's the impedance. And of course, for this one, there is no inductor. So I might as well just cross that one out. So this would say that the voltage I get out is then equal to, and I'll just switch the order here, XC, the reactance of the capacitor, times the voltage you're putting in, divided by the square root of R squared plus the reactance of the capacitor. Now I have a feeling, I need to go back to the question here. 46, right? 46. And they say show, oh, good. Show that the ratio of the input voltage or the output voltage to the input. So the ratio, I got to move this over to here. So this is what I get out compared to what I put in, would then be XC over the square root of the impedance. Now, putting in what the reactance of a capacitor is, it's 1 over omega C. And so this would be R squared plus 1 over omega C squared. And that is exactly what they wanted us to show here in A. And I hope they do a little bit more, because this doesn't really show how it is a filter. Let me go on to part B. I want to say something about the filter, but I think they do it in part B. It says, what value does this ratio approach as the frequency decreases towards 0? What value does this approach when the frequency goes really high without limit? And then even C, at what frequency is this ratio equal to 1/2? Now, I'm hoping my analogy of a voltage divider helped, because I was trying to say here that depending on the value of R2 or R1, we can get any combination that comes out of here between 0 volts and 9 volts. And the same thing here. Now we've moved the voltage to the other side here. So I claim that, you know, because we have an X sub C in the top and the bottom, this ratio can be anywhere from 0 to 1. If the numerator here was 0, of course that one would be 0, then we would get, of course, 0. On the other hand, if X sub C is very, very big, so that we don't even have to worry about the R, when you add an R squared, let's just say a small number compared to an X sub C squared, which is a big number, we can ignore that. Then we just get a ratio of 1. And so this is why we call it a filter, because how much voltage we get out of this depends on this X sub C, and this X sub C depends on what frequency. So if I was making a plot here, and maybe I'll put the number 1 here, and on the vertical axis put the output voltage compared to the input for different frequencies. Watch what would happen at low frequencies. See, at low frequencies, this 1 over a small number is big, which makes this one big. So we can ignore that. And we essentially then have big over big, and they're the same big. So that's 1. So at low frequencies, we basically get the same voltage out that went in. And hopefully that doesn't surprise you, because we already knew way back from chapter 26 that a capacitor wants to get charged, and once it gets charged, it just stays at that voltage till it discharges. And at low frequencies, that's what's really happening, is this comes around here and charges this up, this builds up, and for most of the time then, this has built up a charge that is enough to equal this voltage. This R is doing nothing, and so the voltage out is the same as the voltage in most of the time. Then it switches, and that will discharge it for a moment, but then it'll charge right back up. And so the output voltage is essentially the same as the input voltage. And that's what this ratio of 1 is saying. But watch what happens at high frequencies. At high frequencies, this 1 over a big number is small. And of course, down here, if this is small, you can pretty much ignore it. So you just have this R squared. And so you have small over some number. And if it's really small, so really, really high frequencies, really, really small, this just gets smaller and smaller. This goes to 0. So this is going to taper down to 0 somehow. And so it's going to kind of transition from a 1 down to a 0. And now you're maybe beginning to see why we call these things filters. They're filters because if you were playing, let's say, an audio system, you were designing an audio system, and your input has many, many different frequencies. Let's say you are an audio technician, and this is a band, and the band is playing all these different notes. Some of them are at a high frequency, some of them are at a low frequency. If you pass them through an RC filter, what comes out the other side is the low frequencies are just as strong, but the high frequencies have dropped away. So if you wanted to change the output sound and reduce the treble, but increase the bass, this is how you do it. This is your equalizer. Now, to make it adjustable, you usually put in an adjustable capacitor here, so that as I change the capacitance, I can get the basses louder than the treble. And so I filter it a little bit. And so what actually then comes out here, which then goes to the speaker, is heavier on the low frequencies than the high frequency than what was originally produced. And so that's, again, why we would call this a filter. It's a way of saying, I want to filter out the high ones and keep the low ones. Or it may not be a perfect eliminate them all. You may put it somewhere like here and say, well, that will diminish the high ones a little bit more than it diminishes the low ones. And therefore, I have a higher bass sound to my music. So kind of depends what you are after. Okay, so that being said, you might see why we like to call this a low pass filter, because this is letting the low frequencies pass through. These are the ones that are going to be played at the speaker, the low frequency. And so hence the name low and then pass. We passed on the low frequencies, which is another way of saying we have filtered out or blocked the high frequency. So a very practical device, and like I said, getting a little too much into circuits than physics, but that's, obviously a lot of overlap there, and that's what we're trying to do here. But you can also see why it can get pretty complicated, and to spend a lot of time on this is okay, in these Zoom settings, it's okay for homework, but it's a little too much to spend a lot of classroom time to discuss this in great detail, because that's really for a circuits class. That's what I was saying earlier also. All right, so I'm not quite, I think maybe I finished B. Let me go back and read B here, 46. What did 46 say? It said, what value does this approach as the frequency decreases? So I guess I'd put it this way. As omega goes to 0, the ratio of output to input approaches 1. And so low frequencies get passed on. And then as the frequencies approach infinity, this ratio approaches 0. So we would say the high frequencies get blocked. Now, as a side note, you could probably see it, that back here in our voltage divider, if we had, like, say, R2 really small, so there was very little voltage here, since the two of these have to add up to 9, when this is small, this is big. So these are exactly opposite of each other. So as a sound engineer, I might do this. Besides putting one output here, I might put another output on this resistor, because this would be a high pass filter and this would be a low pass filter. So if I connected to here, I would be amplifying my high frequencies and diminishing my low frequencies. If I put my connection here, I would then, as we said, get the low frequencies, but not the high frequencies. So connecting here makes a high pass filter, and connecting here makes a low pass filter. And I think that the other active figure, this was active figure, what was this, 23, but the one before that, which I think is active figure 22, oh, and it's actually the problem before this. It's problem number 45. They actually have you hook it up to the resistor. So it's exactly the same logic. So this is actually the same answer I'm giving you now is the same answer I'm giving you for 45. I don't know if I should write that in the notes when I send it out, but I'm going to say it now for anybody who's watching the video, is that, hey, the same logic that I'm doing here for 46, I also do for 45. And so 45 is a high pass filter, and this is a low pass filter. Okay, now there's still a part C here. And so part C says, okay, at what frequency is this ratio equal to 1/2? So when does the V out over V in equal 1/2? And so, by the way, coming back to this graph of this low pass filter, I kind of put a little mark here. I wasn't trying to do exactly halfway. It looks like half would be more like down to here. But at 1/2, there's going to be some frequency. Let me call it omega naught. Okay. And this problem C is finding out where it is 1/2. And so kind of a rule of thumb then is we could rate this filter by that frequency. We could say this is a low pass filter at a frequency of, and I need to solve it, but let me just say 1,000 for a moment, 1,000, meaning that all the frequencies below 1,000 are going to be at a half or stronger, and all the frequencies above 1,000 are going to be at a half or less. And so this is has a cutoff frequency of about 1,000. Things more than 1,000 don't get passed on very much. They still get passed on. In fact, the closer they are to 1,000, the more they get passed on. You can see it tapers off to 0. So something around probably 4,000 doesn't really get passed on, but something maybe around 1,500 would get semi-passed on if this number here was 1,000. well, I should actually then do the numbers and find out what that number is. So this is 1 over the, and I'm going to make my life a little bit easier. I'm going to go back to this one here.
Is there a difference between
what?
going back? Wouldn't it be the same?
Yeah,
Error?
well, I was, yeah. Here's what I guess I was trying to say is sometimes you can get bogged down with some complex math when you have something like this. See, I have a compound fraction, I have a square root, and then I have a fraction inside of there.
Yeah, I think when I am going through this problem, I just simplified everything to either negative exponents or, well, yeah, just simplified everything to negative or fractional exponents, and just have a straight formula.
Okay, so yeah, and so here's what I'm getting at. You could do either one, and I was tempted at first to do this one because it has the omega in it, and that's what we're looking for. But I'm going to go to this one first, and then once I solve this for x sub c, then I can get my omega. So I'm going to do it kind of in 2 steps. And that way, if I put the 2 steps together, I got these compound fractions and square roots, and I'm a little, I think I can do the math, but I'm afraid it might be so complex that it's ugly. So I'm just
yeah,
trying
it
to
just
make
sounds
things
gross.
right. So I'm trying to make things easier on me, and more than that, to teach you guys that, you know, sometimes there's more than one way to do a problem, and if there is, do it the easy way. Don't do it the hard way. All right. And so, and you never really know at first. So sometimes you got to just fiddle with it and figure out which way is easier. But looking at this, I really think this might be the easier way. So I'm gonna start with it there, and then of course I'm gonna get rid of the square root. So this becomes 1/4. This becomes x sub c squared, and then this becomes r squared and x sub c squared. And that doesn't look so bad solving for x sub c, the reactance of the capacitor, because then I'll just cross multiply. So this will become an r squared plus x sub c squared equals 4x sub c squared. Subtract a 1 from each side, an x sub c squared, and I got 3x sub c squared. Bring the 3 over and take the square root. So this is r squared over 3 equals x c. In fact, maybe I'll even then just take the 1 over square root of 3 out in front times r and give me my x sub c. And then I'll remember that x sub c is 1 over omega c. So then I will move my omega over to here, which leaves my c on this side. I'll bring my r over to here and my root 3. Yeah. And I hope I did that right. And I didn't have to worry about the fraction until I did that substitution, and I had gotten rid of all the other fractions before that. And so that was kind of what I was hoping would happen. So let me scroll down here to 46. And we know we got A right because we said show that it equals to that. Good. And then we said this as omega goes to 0, V over C. What did they say? V over C goes to 1. Okay, good. And then as omega goes to infinity, this goes to 0, right? And then for C, oh, they did do one more step. They said omega is 2 pi f, okay? So that's always a little confusing if they mean angular frequency or frequency. I interpreted it as angular frequency, and I shouldn't have, because they said frequency. So let replace the omega with 2 pi f and bring the 2 pi over. So they got the square root of 3 in the numerator to 2 pi and an RC in the denominator. And yeah, I can only imagine that solving for omega with this compound fraction, getting a common denominator, squaring it would have been way harder than just those steps. But your call. Sometimes it's nice to. That's why we have those things in calculus like U sub. We don't really care about you, but well, that sounds terrible. We don't care about you. No, but you know, we don't care about the variable u in the problem. We just wanted to put a substitution in there so that something that makes it look easier and we can solve it. Good. Let me go to the chat. Was there anything else? Looks like we are near the end of time. Oh, good. Yeah. Good. Hope that helped, Andrew. And hope that helps next semester too when you're in circuits. I think, Hunter, you said you were going to circuits next semester.
Yes, I am. I'm really looking forward to it.
Okay. Good. You know, in this class in circuits, I always tell students to, especially those who think they want to be mechanical engineering, because this class, at least when we're face to face, can pique a lot of curiosity in people that they didn't know they have. And so they've always been really good with their hands. Maybe they've repaired bikes or cars or worked in the garage, wood shop. And they go, man, I really want to be an engineer. And they come in to their education knowing a little bit about engineering, but really it's mechanical engineering. And they go, I want to be mechanical engineering. I want to, you know, build a gearbox and a transmission. And what they don't have experience with is electromagnetics. And they may not realize how great this stuff is. And I enjoy it more than mechanical stuff. And so it can light a light bulb in them. And they go, whoa. I started with the idea thinking I was going to be a mechanical engineer, but now I think I want to be electrical. Now, of course, I would say the other thing where it's too, there's a number of people who, you know, really struggle with this and say, I don't get it, I don't like it, and I still want to be a mechanical engineer. And that's good. It solidifies their choice that mechanical is their forte, and that you know, that's fine too. And so, and it doesn't change the classes you want to take, whether you think you want to be a mechanical engineer or electrical engineer or computer science. Well, maybe one computer class or two if you want to be a computer engineer, but most of all the engineering and the sciences, it's really the same set of classes. So fine, you know, say you want to be a mechanical engineer, and then after this class, ask yourself again, is that really what I want?
This class is really interesting, actually. I didn't know much about all this stuff before, but I kind of like it now.
See, good. That's exactly what
it's just unfortunate that we couldn't actually do anything like in the labs and all that.
Yeah, you know, something right. I think the students at the end of the semester, they always say that one, the E over M ratio with the electron beam.
It's really cool watching it.
Yeah. They always say that was so cool. And I think I was saying that in the video. I go, I wish you guys could be here and see this live. I hope it comes across on video, because it's just really cool. And usually students in that lab, after they get their data,
they just run around with it,
talking, and then they take a selfie with it. You know, they go, I'm going to take a selfie with this. They got their hand up and got the blue streak, and that becomes their screensaver.
Yeah. No, I ended up seeing that, and I was looking at the screen. I'm like, I sent a video to some friends. I'm like, this is awesome. These are electrons.
Yeah. See, it is really cool. And another cool one is the one you do this week, the oscilloscope. We just play some silly games, but all those knobs, just playing with it, you know, you feel like you're in a jet plane or something. hey, what does this knob do?
Yeah, that one
Hey,
looks like
play with
it
it.
would be hard in person.
What was that, Andrew?
It looks like it'd be pretty hard if we had no experience with an oscilloscope.
Yeah, yeah,
Mhm.
yeah. So I hope, and it's also my hope. That's why many of the lectures you saw me try to bring the oscilloscope into the classroom.
Mhm.
So besides, when you're energizing these inductors or charging up these capacitors, it's nice to actually see a trace on a graph and an instrument that's measuring it in real time, other than, hey, let's solve the equation and make a plot. Of course, they mean the same thing, so hopefully they come across. But it's my indirect way of saying I hope you guys are getting some exposure to the oscilloscope, because it's an important tool that you really pick up more once you transfer. So it's we don't do too much with the oscilloscope, even live face to face, but it's the more you can pick up and the more you can understand oscilloscopes, the better you're off. And actually, I would say the same thing in this chapter 33. You might have struggled a little bit trying to understand the mathematics of phasor diagrams.
Well, it's
And-
simplified easily, so
Pardon me?
it's simplified really easily, so I kind of understand it from that.
Ah, good. Because they really are easy
With
once you
the
understand.
vector representation, it was pretty easy to understand.
Ah, good. Because that's something that is kind of one of these transitions between community college and the four-year school, where the more you can see it, the better. You really got to understand it when you get at that level, and they throw it at you really hard, and a lot of people struggle with it in their junior year or their first year at the four-year school, and so everybody does. But the more you can kind of pick up, the better. So your author and myself aren't trying to completely teach you about phasors, but at least if you get the visual representation, you'll be walking away from here, as you are, Andrew, saying, oh yeah, those aren't so bad. I see the picture. And then now you can carry that into your upper division stuff. I guess another thing too is because phasors aren't covered mathematically in the math sequence. And I've debated for years if they should be, and even had some discussion with some math instructors. They're asking, well, and they're like, well, should we have that as part of our curriculum? And we've always just kind of maybe not, just because it's only really kind of this electrical engineering that needs it, and we kind of teach it anyways, and it's just kind of an introduction anyway. So to make everybody who takes math, do it, is probably one of these things that maybe it should just be explained in your physics or your engineering course. So
Yeah, I don't even know what else it could be used for.
well, anything that comes up with sinusoidal functions. So we'll see it again next semester in 123. Well, we could in 123. And we could also just leave because when we do optics, we're dealing with waves, and waves are sines and cosines. So anytime you start dealing with sines or cosines, phasors are a nice way to kind of visually and mathematically change a trigonometric problem into more of a geometric problem. So you do see it quite a bit in optics.
So I just had a quick question. So I could go, I haven't looked at the syllabus in a second. How bad is the late homework turn-in? Like if I was like 2 days late, would I be Dr. Bunch? Or...
No.
Okay.
No. Just at this point, and I think I'm going to say something Sunday when I send out this week's. I'm going to say something to the effect of, here's the next and last lab. I gave you, I don't know if you noticed, but the lab that I was scheduled to give you this week, I had troubles getting it done, and so I didn't send it to you till yesterday.
Mhm.
Because of that, I changed the due date from this coming Sunday to a week after Thanksgiving, the Sunday after Thanksgiving. I think I mentioned that when I sent it out. I said, okay, just a longer due date. And then the next one, which is Faraday's Law, which I'll send out this Sunday. I'm just going to put that the week after that. And I'll just say something at this point. Just get yourself ready for that exam that's coming up on the
3rd, I think.
3rd. Yeah, and just get things done by the 3rd. I mean, the homework is that way anyways. The homework you just have to get done by the 3rd. But I would say the same thing for the labs. Just get the labs done by the 3rd and kind of work on your busy schedule. Because I know you have other classes and work and holidays, and this always just makes such a busy time.
Sounds good.
As long as we can learn the material at the end, that's the goal.
Yep. That's
Well,
heavy lifting.
Are we gonna have homework for chapter 34?
Yeah, and so something else I got to figure out tomorrow and send it out to you Sunday, or maybe I'll do it Sunday morning. But I need to look at what sections to cover and then what homework to do. I won't have you turn in any homework, that's for sure.
Okay.
What I will do
Because,
is
yeah, there's
point
just
out some.
video about like Maxwell's equations, right?
Yeah, and I'll just make a comment about that. Maxwell's equations, the title of that chapter is misleading because Maxwell's equations, there's 4 of them, and 3 of them we've already done. So the first one was Gauss's law, we already did. The second one's Faraday's law, we already did.
Yeah.
The third one is Gauss's law of magnetism, which we already did and didn't do much with it. There is one more that's what's another one? Oh, Ampere's law. And so Ampere's law we already did, but what Maxwell does is 2 very important things. The first thing he does is he extends Ampere's law. He shows that Ampere's law is, as we've learned it so far, is not complete. And so he throws in another term. So that's the big learning lesson for chapter 34. The other thing why he's given credit is even though we've technically done all 4 of Maxwell's equations, I'll say them again. We did Gauss's law, we did Ampere's law, we did Faraday's law, and we did Gauss's law of magnetism. So technically we've done them. However, what Maxwell did really, really nice, and why they're called Maxwell's equations. Did you catch that? They're not Maxwell's laws.
Yeah, he just
Not
took
Maxwell's ideas. There's Maxwell's equations, because Gauss's law, as you learned it, was described by Gauss in words, not equations. Vector calculus did not exist. Faraday's law, as you have learned it, was described in words, not in equations. And so the real claim to fame of Maxwell's equations is he was able to take these 4 main ideas of electromagnetism and put them into an equation form. So we have already done Maxwell's equations. We haven't been calling them Maxwell's equations. We did not want to try to do Faraday's law without math. That is not a good way to teach it. But we actually have done Maxwell's equations because we've done Faraday's law in vector calculus form.
So chapter 34 should really be just expanding Ampere's law a little bit and then like completing it and then just kind of reviewing the previous 4 laws.
Yes, and then one more thing. The extra term, as you said, that we add to it, has some really major consequences that you'll see are the idea of wireless communication. So, and that's a big deal, obviously. So the way we've learned our electromagnetics, we're almost complete, but we're missing one term. We're missing that discovery by Maxwell. And without that term, you can't have microwaves or radio waves or optic waves. So we got one big more piece to learn, really.
Yeah.
And so it is a little piece, but it's got a major consequence. Yeah.
Yeah, that sets us back like 100 years without that.
Yeah, exactly. Yeah.
Did he also figure out all the constants too? Like, or he had to, right, in order to put in equations, right? Or
No. The permittivity of free space. Well, so things were measured. The data was there.
okay, so he was putting in taking the data and then translating it to an expression or equation.
Yeah. So like let me just take Faraday's law, which says the EMF, so that's the voltage, okay, is equal to change in flux. So there wasn't really a good set of calculus that had an integral with a B dot dA. There was none of that kind of symbol. You just wrote it in words that it was the change in flux. And so you kind of looked at the flux and you said, well, this magnet has 4 Webers, and then you pull it away. So the change is 4. And you took it away in about a half a second. So, all right, so 4 Webers divided by half a second, that's 8 Webers per second. All right, so the EMF on average is, so it's not to say they weren't doing some math, but it wasn't calculus. It wasn't vector calculus. It was more of an algebra.
Still cool.
Yeah. So the ideas, it's interesting that the ideas of flux and vector calculus were formulated in the physics with pictures and diagrams before somebody was really able to kind of put that in equation form. And that's where Maxwell comes into play. So I think this is about 1850. I think Maxwell's equations he writes out completely in 1865. And so that's where vector calculus and the notation as we see it today, and the things like and we really haven't done it in this class, but if you've taken your math 200, you hear words like the curl of the vector field, the gradient of the scalar field, the divergence of the vector field. And so these kind of things were just getting in words and drawing pictures, but really didn't have the kind of form that you learn in your math 200 class today. So again, that's why it's called Maxwell's equations, not Maxwell's laws. He didn't discover all these electromagnetic connections. He took these electromagnetic connections and made them into the equational forms that we have today. Which, and by the way, there was a debate at its time. People said, well, that's not a better form. I like the form I've been using. Okay, so that's why it was called Maxwell's equations. These are written Maxwell's way. So these are Maxwell's equations. All right, but I don't like that. So I don't want Maxwell's equations. I don't want them written that way. I like them written the old way because this is the way I learned. So that's where it got that phrase. These are Maxwell's equations.
That part sounds like the permanent status of all people who try and do things.
Yeah, and there's a phrase in science that is at least half true, sadly, that new theories don't get accepted as much as the older generation dies away. And so like Einstein's theory of relativity was really hard to accept for, it's new, it's crazy, it still has to have experimental tests. But even when that first experimental test come, it's like, I don't know. I've been doing this for 50 years, and you give me one test, do another test. And global warming's the same way.
yeah, that's fun.
It's especially 20 years from now, the diehards of no global warming that were kind of duped into global cooling in the 70s, because in part science fault. You know, they were telling us how much the planet was cooling, and we're entering an ice age in the 70s, and then that all changed in the 80s. And so you do something like that, you know, you just like, wow, who knows what, you know, you're just going to blow it off and say, those scientists don't know what they're doing. And well, and you see it now with the coronavirus and masks. I mean, we know the masks really work, but at first we didn't know that. And so I remember, you know, Dr. Fauci at the beginning, you know, because my wife wanted me to wear a mask, and I was like, look, Dr. Fauci himself is saying masks don't help. So I'm like, I'm not wearing a mask. He said no. Well, new information comes out, and you know, now that we're 8 months into this thing, there's no doubt that a mask is important. So it's like, okay, I wouldn't go outside without a mask. But, yeah, at least I'll carry it in my pocket when I'm walking my dog, so if I cross somebody, I'm like, oh, well, pull it up. So, you know, it's different, but there's still those people who are going back to the very beginning and saying, well, they first said no mask, and now they say new masks. So they don't know what they're talking about. So I'll just do it my way. And that's what science is. It takes time. Mm-hmm. And vaccines the same way. You know, these these vaccines coming out are amazing. First of all, they've never been engineered this way. They've never been just designed from a computer. That's amazing. And so, I mean, one thing the Chinese did really well is that they did the DNA code of this and then just gave it to the world and say, do what you want. And Johnson & Johnson and Pfizer, they took that DNA code. They made a messenger RNA just from a computer code. And they have not changed it since they first made it back in April. But nobody took the vaccine in April. Nobody wanted to take the vaccine in April. It hasn't been tested. But now that they've gone through phase 3, and you see it again, there's still, I'm sure there are many people out there who still wouldn't trust it. I'm ready to trust it. So, I mean, if it did all these tests of phase 3, I'm good with that. But I would have never taken it in April. Like the Russian vaccine, you know, they claim. But you see, but on the other sense, science was actually right in April. You know, they actually had a vaccine back in April, or maybe it was closer to May. But they had it tested on animals, and then and human studies take 3 levels, and you didn't want to rush it. I mean, if we did, you could save some lives, but you wouldn't have trust. Mm-hmm. Well, we still don't have trust. So.
We already kind of rushed it too, if I'm not mistaken. Normally, like, those vaccines take a lot longer than like the 8-month turnaround time we've got right now.
Oh yeah.
All of us have been way accelerated.
Oh yeah, this is amazing. This is amazing. Although I'm not a big fan of Donald Trump, you got to give him credit for this. This is just amazing. They took that, they threw $2 billion at the pharmaceuticals and say, you make this vaccine, you make it by design, we'll give you $2 billion, you can do anything you want, you make these, you do trials, and we cannot wait the typical 3 to 4 years for a vaccine. You get a vaccine in as fast as you can. Yeah, man. And so we've broken all kinds of records. We've designed a vaccine just from a DNA code, and we've got it past clinical trials in under 8 months. That's amazing. Yeah, and they say they're going to start vaccinating teachers in phase 2, so they'll do first responder first. So I'm thinking I might get a vaccine by January. Well, late January.
That'd be solid.
Yeah.
If that happened, they would let us go back. Probably not, right?
Probably not until the general public's got it.
Yeah, I think they'll be waiting until general public, and and the other thing they did amazingly well is they trusted it so much that they've already made 40 million doses, even though they haven't even tested it completely or got approval.
Yeah.
Mm-hmm.
I I mean, there's already 40 million. Now, that's not enough, obviously, for the whole United States, but that's enough for emergency responders. So emergency responders are probably going to be vaccinated before into December.
I know there are two out right now that work, the Pfizer one, and then I can't remember the other.
Moderna.
Yeah, I think are they releasing both of them at the same time, or just like, hey, if you can get your hands on either one of them, get it done? Or I don't know if anyone does it.
Yeah, well, as soon as they can. So they're only days apart.
Mhm.
So I think they'll the same thing. One of them finished first. I think the Johnson & Johnson one finished first, or Pfizer.
Pfizer did first, and then
Yeah.
Moderna came out second.
Moderna's just a couple of days. So I think the FDA is probably going to approve the first one in a couple of days and the next one a couple of days after that.
Wow.
And the other one, the third one, I'll even say the fourth one because
AstraZeneca is getting close to, I think.
yeah, see, that one got stalled. In fact, my college roommate, who's a chemist he teaches up in Idaho, he volunteered to be one of their test people. And so he got that vaccine, and then they had that person get really sick, and they stopped it for 2 weeks. And he was a bit nervous during those 2 weeks. He was like, okay, what's going on? And then the person who got sick, they found out was sick for other reasons. And it had nothing to do with the vaccine. So they picked it up. And so he was telling me yesterday that they're just 2 weeks behind. He goes, in 2 weeks, they'll probably get approval too. They'll be sending their data for approval. And then the Oxford one, which has, that's obviously UK. But they will, I'm sure, file for approval in the US also, would be the fourth one. And that one, I think they're only days behind. So we'll have a third one from Oxford in a couple of days. We'll have a fourth one. And some of these have benefits over the other ones. I think the Oxford one is showing a stronger promise. I'm not sure about this, but a stronger promise for the seniors and senior citizens. So you might have some options. But I think in reality, it might be just logistics. And they'll say, all right, send these brand to the West Coast, send these to the East Coast, put this in the middle of the country. Let's just get everybody with a vaccine, and we just got to get it out there. And if you have one that's 95 and you have one that's 96, so be it. You just need a vaccine.
Yeah, it might come to distribution too. I know like Pfizer's has to be at like negative 110 or whatever on transportation and stuff.
Yeah, that's going to be a challenge.
Yeah.
Yeah. But it sounds worse than it is, because that's no different than dry ice.
Okay.
So you could pack them into big trucks and then load it with dry ice.
Oh, that's not. Just get a big old semi.
yeah, big old semi, and So to actually get a freezer that gets that cold, that's a pretty big deal. But to get some of these ice companies, like for you guys, when I did the air thermometer one, which I guess we do in Physics 123, so we didn't do it this semester. I just go down to Santa Barbara Ice, and they've got a big old freezer. They make their own dry ice, and actually I don't think they make it. I think they bring it in. So, but they've got a big vat there, and I can get as much dry ice as I want. And so you just got to get all these ice companies start making ice so they can get their vaccines transported.
All right,
I don't think the news did a fair job with that, because they were saying it was like really hard, and I was like, it is a challenge, but once you have enough dry ice, it's not a challenge. So the challenge is getting enough dry ice.
All right, that's solid. Yeah, I'm happy. I know I haven't had enough time in physics to catch up on all of it.
Yeah. If it was any colder than that, they probably wouldn't have pursued that vaccine, because it would have been too hard. Because dry ice is a normal way. In fact, even the ice cream man that comes around my house, that's what he does. He packs all the ice creams in dry ice. I guess it's just easier, because ice isn't cold enough to keep ice cream cold. And of course, dry ice is great because it just evaporates into carbon dioxide.
Mm-hmm.
However, when I buy my ice cream sandwich from him, it is rock solid. I mean, I buy that thing and I go, okay, I'm not going to try to bite into this for about 2 minutes. I just got to let it warm up a little It is cold. And I feel like I'm trying to chew on a brick.
Fun.
Yeah.
All right. Well, hey, I gotta go. Thanks so much for help. I will. Next Friday we have off, right? So there's not gonna.
Oh yeah, okay. So I'll tell you guys. Here's what I'm thinking: that next Friday, because it's a holiday, and I know it'll have a lot of impact on people's studying patterns and where they are, and myself included. And since you have your exam the Thursday before the next Friday, I think what I'll do is take that Friday Zoom and move it to Monday. So that'd be Monday the 30th.
Okay, so we'll have a Zoom.
So we'll have a Zoom before the test, but it'll be after the holiday weekend.
Okay, awesome.
That
Then,
works for me pretty well too.
Oh, good. I'm glad that works for you. Yeah.
so that'll just be like you'll send that one out, and then we'll get.
Yeah,
that.
and I'll explain that on Sunday. I'll say, hey, this week's Zoom is different because of the holiday.
Fun. All right. Well, thank you so much. Have a good weekend.
All right. Take care. See you guys.
Thank you very much, Mike.
Will chapter 34 be on or the third test or the final?
It'll be on the third test. Very little of it, and how much. That's what I'll decide tomorrow. I'm going to look at those sections.
Okay,
I'm
yeah.
going to look at the video recording.
Email.
And I'll add that then in my description on Sunday. So as you guys start to get ready for the exam, you know how much and what problems, of 34 to do.
Okay, sounds good.
All right. Take care, everybody.
Bye.